Hello and welcome back to Precalculus1, section 3.4, Exponential and Logarithmic Equations, with the punchline. The most important formula of the chapter will have, you will have to use the most important formula of the chapter in this one for pretty much every problem. And that is, what's the most important formula? Okay, well that's just part of it. Exponential form converts into logarithmic form. So, you are familiar with the fact when you're solving the equation. You are familiar with the fact that you are supposed to use opposite operation. So, if you have x plus 3 equals to 5, if you subtract 3 on both sides, right, you will get x alone, and you get 2, and the problem is solved. That's the solution. This idea of using opposite operation, 5x equals, I don't know, 95. You use opposite operation, which is divide by 5, both sides, and you get x equals to 19. Again, that's the solution. So the problem had, in the first case, addition. You use the subtraction, which is opposite operation. 5x was the multiplication. You divided by 5 to get x alone. Now, if you have, say, 2 to the x is equal to 19, you will have to use opposite operation. An opposite operation is the log, and you are using conversion in this case. So you will convert exponential equation into logarithmic, and what you see immediately is that log of 2 of 19 is equal to x. Now you can use change of base to calculate log 2 of 19, which is, you can do log base 10 of 19 divided by log base 10 of 2. And when you punch those numbers in the calculator, you obtain an answer. So let's see what we get. So log 19 close parenthesis divided by log 2. You should get 4 point. Make sure you're having 4 decimals. 4.2479 as the answer. So the same type of thinking that was used in your previous courses to solve basic equations is used now, except the opposite operation of exponential function, right, would be logarithm, and opposite of log is exponential. So we are having, we have to use the opposite operation of whatever we have. So if I have a basic problem like log base 2 of x is equal to 5, we are going to write this in exponential. 2 to the 5 is equal to x. And now 2 to the 5 you can calculate, so x is 32, and the problem is solved. So this creature here is called exponential equation. Because clearly it's an exponential form, exponent x is unknown, and you will see that we use log to solve it. The creature on the bottom is called logarithmic equation. and we used exponential form to solve it. We used conversion formula in both of these cases, and that goes for the rest of the lecture, rest of the section. So now we're going to take a look at exponential functions in detail, and then we'll take a look at logarithmic functions in detail. Next class is 3.5, which is word problems, and the word problems will put all of that to work in the applied sense. So let's start with exponential functions. We are going to repeat those basic exponential functions from before. So say you have 2 raised to the x is equal to 16. Yeah, you can do log on this one, sure. But there is actually a much faster way to do this. 16 is a number that has a base 2. So I can rewrite this problem. 2 to the x is equal to 2 to the 4th, from where x is equal to 4. This method is called solve by comparison. You see, you have an output over here, maybe in blood here. Same base. You can't use this if you have 2 to the x equal to 9, because you can't write 9 as 2 to some exponent. But 2x to 16 is okay, because you can write 16 as 2 to the 4th, and then you see you have a same base. In order for equal to work, and you have the same base, right? If 2 is the same as 2, then 4 and x better be the same to have the same things on left and right. So it's a really interesting way to solve these equations. Another example would be, let's say, 3 to the x is equal to 1 over 27. You immediately recognize that 27 can be written as 3 to the 3. So you have 3 to the x is equal to 1 over 3 cubed. Now you will bring this 3 cubed up. So 3x is equal to 3 to the negative 3, right, when it goes from the denominator to the numerator. And x equals negative 3. This is also solved by comparison, because we are comparing left and right side, and we just see that x must be negative 3 in order for left side and right side to be the same. Can you do this by conversion? Yeah, conversion solves it. But conversion is maybe too much work for a problem that can be quickly done by comparison. Other way. We use conversion to write log base 3 of 1 over 27 is equal to x. log 1 over 27 divided by log of 3. You can use ln as well. And your answer in the calculator better be negative 3. But if we can solve it by comparison in few seconds, there is really no need to go through conversion. No coffee. Now, let's say you have 3 to the x is equal to 12. See, we can't solve this by comparison now, because 12 is not a power of 3. The powers of 3 are 3, 9, 27, 81, right? 3 to the first, 3 squared, 3 cubed, 3 to the fourth. 12 is not on the list. So we can't solve it by comparison. We must use conversion. we must use conversion. So log 3 of 12 is equal to x. ln 12 divided by ln 3, and we calculate that. We know this has to be 2 point something, but we don't know exactly how much. So ln 12 divided by ln 3, 2.26, 19. That 5 will change 8 into a 9. And the problem is solved. Now what I'm going to do is I'm going to check, because I can. 3 raised to the 2.2619 is equal to what? So 3 raised to the 2.2619, I get 12.3 zeros and then 5, 3, 4, and so on. You see this is extremely close to 12. And it's not exact because we didn't copy the rest of the decimal numbers there. We wrote only 4. But this is good. I mean, this is the best we can do. I mean, we can do better, but let's call this best. So we've seen 2 basic methods so far. Comparison method, which is you make the base on the left and the right side the same base. So same base, base 2, and same base, base 3 in these 2 examples. And then simply by comparison, since I have the same bases, I have to have the same exponents. Now, can I make this hard? The answer is no. Can we make it annoying? Yes, right? So you can have on one side 3 to the 2x minus 1 as the exponent is equal to 1 over 81. So this would be somewhat annoying, right? Problem. What do I write 81 as? Three to the negative 4th. Because it is in the denominator, 81. When you bring it up, it will have negative exponent. And 3 to the 4th is 81. So 3 to the 2x minus 1 is equal to 3 to the minus 4. And now we compare. We get 2x minus 1 is equal to negative 4. And now you have a very simple equation that you can solve for x. So 2x is equal to negative 3. And finally, x is equal to negative 3 halves. And that's the answer. Negative 1.5 or negative 3 halves. So if you put negative 3 halves for x in the equation, you better get 1 over 81. Let's see. So 4 to the 3x plus 2 is equal to 2 to the x minus 1. It's a spicier version. I get some water over there. Right. So let's consider the problem together. Look at it. 4 I can write as 2 squared. So this becomes 2 to the 2, 3x plus 2 equals 2x minus 1. And now comparison. So 6x plus 4 is equal to x minus 1. Move x to the left becomes 5x. Move 4 to the right becomes negative 5. X is negative 1. So here's your 4. Exponent stays the same. And then this is where we say same base. We compare exponents. Because it's the same base, there is equal sign in between. So sometimes you have to work with the left side, sometimes with right. And probably the trickiest problems in exponential equations would be where you have to massage both sides. Say 9 to the x minus 3 is equal to 1 over 27. Right? So what is the common base? 3 for both sides. So express each side as a base 3 and then do the rest. So 9 can be written as 3 squared, and then we have x minus 3 exponent from before, equals to 3 to the negative 3. Right? We know that 27 can be written as 1 over 3 cubed, and then when it goes up, it changes the sign on the exponent. So when we compare, we get 2x minus 6 is equal to negative 3, 2x is equal to 3, and x is equal to 3/2. Again. The issue is when you cannot compare, you use conversion. So 4 raised to x minus 6 is equal to 9. Well, you use the conversion. Use conversion because no common base. There is no common base for 4 and 9. 4 is base 2, 9 is base 3. So no common base. So we have to convert this into log 4 of 9 is equal to x minus 6. I will write one more time the conversion formula here. A to the b equals c converts into log a of c equals b. So you see that this b is the x minus 6, which is b for the log form is x minus 6 on this side. So now you use your abacus to figure out log base 4 of 9. So that will be ln 9 over ln 4, or log 9 over log 4. And hopefully you have that it's 1.585 and then 0. is equal to x minus 6. So to get x alone, you add 6 to both sides, right? So x is equal to 7.585. And that will be an answer for this particular problem because we had to use conversion, right? It's not a whole number. Slightly more annoying version. 3 times 2 to the 2x plus 1 minus 6 is equal to 4. What would be the first step? What do I have to do first in this case? I have to fish out this, right? Which means I have to remove 3 and 6. Which one do I remove first? 6. So we go plus 6 on both sides first, which gives me 3 times 2, 2x plus 1 is equal to 10. Divide both sides by 3 to get exponential part alone. So 2x plus 1 is equal to 10/3. Now we can use conversion. Please note that conversion goes a to the b equals c. There's no other stuff before and after a to the b. It's by itself on the left. Therefore, you have to remove all of the extra things and leave the exponential function by itself on the left. So now we use conversion. Log 2 of 10 over 3 is equal to 2x plus 1. We use the change of base formula. To calculate the log. Hopefully you get 1.737 is equal to 2x plus 1. And now you subtract 1 on both sides. So 2x is equal to 0.737. And then divide both sides by 2 to get the answer of x equals to 0.3685. So when the problem tends to, when the problem gets more of these other than exponential, you have to isolate exponential and then use the conversion. So if the bases are compatible, right, you have the same base on the left side and the same base on the right, you have to use that base, right? And you can do comparison. Other cases, use conversion. Now there is an evil case, as always is, right? And the evil case is a mix of exponential function with a polynomial. That one cannot be solved. All right? Cannot solve that one. So if you have, let's say, 3 to the x plus 5 is equal to x minus 7. Cannot solve this. But let's say it cannot solve it by algebra, like we did above. And the reason is, if you use conversion to free up this, you will bury this. You see, if I go and use a conversion, the conversion will say log 3 of x minus 7 is equal to x plus 5. So you freed up x plus 5 and you buried x minus 7. There is no way to use the conversion in a way where all x's will be on one side and just numbers on the other. You cannot achieve that with the example below. So all of the techniques and methods that we did up to now are completely useless. The only way that you can use now to solve this is to graph and look for intersection point. So these problems are solved by graphing. If the two functions intersect, the x coordinate from that intersection is the solution. So on my calculator, I'm going to go into y equals, make sure there's nothing else there, and then I will type 3 raised to the open parenthesis x plus 5 close parenthesis, and then I'm going to go to the next function, to y2, and type x minus 7. And then hit graph. So what happens in this particular case, we have exponential function, which is right here, and you have your linear function that goes like this. So this is your x minus 7, and this is your 3 to the something. What do I have? X plus 5. In this example, functions do not cross, implying no solution. That's a possibility. If they don't intersect, if they don't cross, then there is no common x and there is no solution. Now all I needed to do is to make it equal to minus x minus 7. Then this line would turn and will go this way, and it will intersect, and whatever intersection x gives, it will be a solution. So, to classify all of these equations that we covered so far, all equations, apart from the evil ones, can be solved using conversion. Because conversion for exponential form is like subtracting 3 on both sides for basic equation. So we have conversion. And that works all the time except in these cases. And then we have comparison one. If you can make base on the left and base on the right to be the same, well, in that case, you manage to then you can match the exponents. There we go. So if you manage to get both sides to have the same base, then in that case you are allowed to match the exponents. And that would be comparison part. Let's see if Mr. Blitzer has anything else for us over here. Done. Oh, I never mentioned, we haven't done a single case with e. So e to the 2x is equal to 19. What should I do? What should I do? Convert. So what do I write? ln 19. So we convert as a log base e of 19 is 2x. But then we know that log base c is ln. 19 equals 2x. Remember that log base c of x is ln x. That's shortcut notation. So now what's ln 19? Is 2.9444 equals 2x, and then divide by 2, x equals to 1.4722. Do we all have the same answer? both have the same. Now I want to introduce you to a quicker way of solving this. We are going to use it a lot on Tuesday, right, when you do 3-5. And that is when you run into these equations, e to the something, right, 2x equals 19. Generally what people say, ln both sides. Ln both sides. It's not multiplied by ln. That has no meaning. You ln both sides. You apply log to both sides. And now on the left-hand side, they cancel because they're inverses of each other. And you are left with 2x. On the right-hand side, you have ln 19, which is 2.9444. And then immediately x equals 1.4722. So the notion of ln both sides to actually cancel out e. Now you can always do the conversion. And then just solve for x. Another one? For good measure? Yeah, that's the spirit. Two e to the x plus 3 is equal to 12, whatever. What's the first step? Divide by 2. Good. So we have e to the x plus 3 equals to 6. Now what? ln both sides, right? ln both sides. We have x plus 3 equals to, and ln 6 is 1.7918. Take away 3 on both sides. X is equal to what? Negative 1.2082. So you ln both sides and follow up. The last batch of problems for exponential, and then we move into logarithmic, is batch of problems which have the bases that don't match. So for x minus 3 is equal to whatever, 6, x plus 2. And there is an interesting way to solve these problems to get exact answer. And you can punch that exact answer in a calculator and get a different answer. I mean, the approximate answer in decimal. So what do I do here? I ln both sides. And then we use property which says that ln x to the p is p ln x, which means that all of these exponents can go in front. So I have x minus 3 times ln 4 is equal to x plus 2 times ln 6. And now you solve for x. You're probably going, how the hell I'm going to solve for x? Well, guys, ln 4 and ln 6 are just numbers. They're constants. So you distribute those, put all of the terms with x on the left and all of the terms without x to the right, factor out x. So it's a little bit of algebra hike, but it's really doable. So we have ln 4 times x minus 3 ln 4 when we distribute ln 4 on the left. When I distribute ln 6 on the right, I have ln 6 x plus 2 ln 6. Now move the term this way and move this term that way, because we want to have all the terms with the x on one side and all of the terms without x on the other side. So I have my ln 4x, and now minus ln 6x is equal to 2 ln 6 plus 3 ln 4. So I grouped all of the values with x, and now I factor out x, which gives me ln 4 minus ln 6 is equal to 2 ln 6 plus 3 ln 4. And now we divide both sides by this ln 4 minus ln 6. And we're done. That's the answer. X equals, so this is the final answer. X equals, when divide both sides, right, this left side cancels. You have 2 ln 6 plus 3 ln 4 divided by ln 4 minus ln 6. There we go. Now that's exact. You can punch this in the calculator and it will give you decimals, if you care about decimals. When should you care about decimals? when you work with money. Money has cents, right? So you present cents, and you present 2 decimal places in that case. For all other calculations, we like to keep at least 4, because these functions pick up error quickly, and that makes issues and problems. Okay. Actually, why don't you try one of these interesting problems? How about 3, the 2x minus 1 is equal to 4x plus 5. Let's take a look. Together we are going to ln both sides and then just follow algebra from there. We have 2x minus 1 times ln 3 is equal to x plus 5, that's the exponent that drops down, times ln 4. We are going to distribute everything. I'm getting 2x ln 3 minus ln 3 is equal to x ln 4 plus 5 ln 4. So all I did is I ln both sides, and then I used the property of exponents that takes the exponent and drops it in front of the log. So there's the exponent 2x minus 1 in front of ln 3, and there's the exponent x plus 5 in front of ln 4. That property was studied last class. Then we use basic distribution. So now, once we distribute ln 3 and ln 4 to both terms, we have 2x ln 3 on the left minus x ln 4 on the left is equal to 5 ln 4 plus ln 3. And now we factor x on the left. We are left with 2 ln 3 minus ln 4 equals to 5 ln 4 plus ln 3. And finally, when we divide, x is equal to 5 ln 4 plus ln 3 divided by 2 ln 3 minus ln 4. Aren't you glad you got up this morning? This has to be the highlight of the day. I mean, no matter what. Look how awesome this is. Especially if someone asks you, hey, what's new? On a napkin, right away. Don't give them a chance to interrupt you. They might never talk to you again, which is a plus, obviously. Yes, this is correct. All right. Ooh. I forgot about these. I thought we're done with exponential equations. No, 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 no. There are exponential equations that are disguised as quadratic equations, which you can turn into quadratic equations and then solve those. Eesh, look at that. Let's start with the vanilla example of e to the 2x minus or plus 5 e to the x plus 6 equals 0. Start there. I hope you see that this looks like x squared plus 5x plus 6, right? Except it has this e to the x everywhere. So what we do is we make a substitution. U equals e to the x. And once you have the substitution u equals e to the x, this problem becomes u squared plus 5u plus 6 equals 0. So each e to the x became u. And now the problem is transformed into a basic quadratic. You can factor this, right? What are the factors here? U u plus 2, u plus 3 equal to 0. You solve each one of these using zero product rule, right? So u is -2 and u is -3. Are we done? No, because it's variable u. We need variable x. The problem was stated as a variable x. So we have to go back to original variable and compute what x is. No one cares about u. So at this point, you go and you replace u's with e to the x. And at this point, if you studied basic exponential functions, you know that these have no solution. Because exponential functions graph like that, and the functions -2 and -3 would graph below x-axis. They never intersect, so they don't have common x's and therefore no solution. But let's say you didn't study that aspect, you didn't catch that. Well, you will ln both sides, and then ln of e to the x is equal to ln of -2. Ln e cancels, so x equals ln of -2. Well, at this point, you might study, maybe you studied logarithmic functions and you know that the domain of logarithmic functions is from 0 to infinity, yet you have -2. That's not in the domain. Therefore, this is not something that can be calculated in the real domain. So, that's a second stop where you could go and say no solution. Finally, you take your abacus and you punch ln -2 and you get error. Depending on which calculator you use, some calculators will actually give you a complex solution. We dealt with complex numbers. We know complex numbers exist, 3 plus 2i. This has a solution in a complex world. So depending on which calculator you use, your TI-83s and 84s and these basic calculators, they should all return error because they deal only with the real domain. However, TI, I think 92, 96, and there are some titanium editions and so on, they will actually give you complex value for this thing. But it's not real. I mean, you still see I in the answer and you know it's not real, so you can't claim that that's the answer. So, not in the domain, no real solutions. No real solutions. The -3 will suffer the same fate, right, of no real solution. So this particular equation, which I picked, has no real solution. I'll go through this problem one more time, and then we can finally switch to logarithmic. We're starting problem with e to the 2x plus 5, e to the x plus 6 equals 0. We realize that this is of the form x squared plus x plus a number, which is quadratic. And we use substitution, u equals e to the x, to go away from e to the x and replace each e to the x with u. So we have u squared, we have 5u, and plus 6 equals 0. Then you perform whatever witchcraft you know to factor it. If you know factoring, go ahead, do it. If you don't know factoring, you will use quadratic formula. So whatever works for you to get this factored and done. And then we solve each one of those, and we obtain u equals -2 and u equals -3. But we can't leave the problem in terms of variable u. This is what you might want to say, I don't care about u, I care about the x. Which means put x back by replacing u with e to the x. And then you have this equation to solve. Solve by ln both sides, and that might or might not give you a solution depending on what number you have. And problem is solved. Done. Questions, concerns? It's awesome when this is so clear that there's nothing to add, nothing to ask. So we should have tests right now so you can get your hundreds and just move on. Right? Exactly. There we go. People don't smile enough in this class. I'm really concerned. There we go. I can break you on the individual level, but I can't, right? I can't reach the entire class at once. That's okay. Let's talk about logarithmic equations, see if that's going to make it better. I hope it will. So logarithmic equations. We are going to have comparison again, conversion again, and in addition, we are going to have those formulas that compress multiple logs into single log from our previous class. I did mention that you need to study that so that you can survive today, and here they are. But let's start with the vanilla examples. So how about log 3 of x is equal to 11? There's nothing we can do here other than conversion. Base is 3, exponent is 11, and we have x. Now 3 to the 11 is going to be huge numbers, so we're just going to leave it like that. But that's the solution. These problems are very quick when they don't have any extra features, right? How about log base 2 of x minus 5 is equal to, I don't know, 8? What's the conversion on this? Anyone? 2 to the 8 is equal to x minus 5. How much is 2 to the 8? 256. Equals x minus 5. So x is 261. Very quick, as you can see. Now, interesting problems in this part are problems where you get to compare logs and then compress, then compare logs. So we start with just compare logs first. So if you have log base 2 of x minus 5 on one side is equal to log base 2 of x plus 8, or 2x plus 8 on the other side. We have the same rule like we have for our exponential functions, equations. You have the same base. Same base means you can compare the logs. Same base implies compare arguments. These things are called argument of the log. Whatever is there, it's called the argument. We have the same base, therefore x minus 5 is the same as 2x plus 8. Move x this way, you get x. Move 8 is negative 13. X equals negative 13. You walk away. Except you have to be very careful. Logs produce extraneous solutions. Right? So is this a good solution? The answer is hell no. Mathematics gave us negative 13, but if you plug negative 13 to check, this is what happens. Log base 2 of negative 13 minus 5. Guys, that's log of negative 19. Negative 18. Yeah. If you type this in a calculator, the calculator is going to explode. So, no solution. The only number we got is negative 13. But if you try to plug negative 13 back, you get negative 13 minus 5, it's negative 18. And same thing happens on the other side. You cannot take log of a negative number. So this equation has no solution because the only x we got is no good when we plug it back in because it produces complex values. So we don't have a solution in the real world, in the real part of mathematics. Now, in order to ensure that every single one has the answer, I'm just going to steal a few problems from the textbook. So here's another example. Now this one is going to ask us to compress and then use the conversion. So what we have is log base 2x minus 6. This is problem 75. So log base 2 of x minus 6 plus log base 2x minus 4 minus log 2x, log base 2x, equals 2. Now, I'm going to compress this into a single log. So all of these two will be log base 2 of x minus 6 times x minus 4. We still have minus log base 2 of x equals 2. Now, these guys will compress further and we'll have a division introduced. So it's x minus 6, x minus 4 divided by x equals to 2. And we can finally do the conversion. So in a conversion, it's base raised to the exponent is equal to the argument of the log this is not 4, it's x. And now 2 squared is 4. So 4 equals FOIL. We get x squared minus 10 plus 24 over x. And finally, when you cross multiply, you have 4x is equal to x squared minus 10 plus 24. The first rule of solving quadratic equations is to make everything equal to 0. So, x squared minus 14x plus 24. Hey, where's my x? So 4x moves, becomes a negative, and 10 is negative 14, and then 24 solve, this stay. Alright, great. So this is now equal to 0. Now you factor this, and you get x minus 12, x minus 2. Equals 0. So x is 12 and x is 2. Now you have to check this. You have to check both solutions. There's a reason why this problem is 80 points on the test. It's a lot of stuff here. So we have our candidates, 12 and 2. Plug in 12. 12 minus 6 will give you 6. 12 minus 4 will give you 8. Over here is 12. All those numbers are positive. So this looks promising to be an answer. Now you can go compute exactly each one. So I'm going to label x equals 12 as a good answer. Now we analyze x equals 2. If x is equal to 2, this becomes negative 4. I don't have to go any further. I'm done. It's checked out right away, right here. Because you cannot take log of a negative number. Study the domain of logarithmic function. It starts at 0 and goes to positive infinity. So you cannot plug in negative 2. You cannot plug in negative 4. You cannot plug in any negative value. So when I took that 2 and I put that 2 for this x, I get 2 minus 6. That gives me negative 4, and that immediately kills it. There is another one over here. 2 minus 4 is negative 2. And then this one will be positive 2. But that doesn't matter that you have this one that works, where these two are both complex, right? So the check did not check out for x equals 2. So that's the one we have to eliminate from the list of solutions. Is that it? I guess we'll continue on Tuesday. Study properties of logs, especially 3-3 stuff. so that we can do more of these problems where we condense and work on homework as much as you can. See you all on Tuesday.